No, just over here. Thank you. Okay, so the title of my talk is Hierarchical Reinforcement Learning for Interactive Systems and Robots. I guess it's a bit long, but I hope to give you the main ideas of this learning framework, which is different from the one we mostly heard yesterday. Yesterday we heard a lot about supervised learning, which is one machine learning framework out of several. This is another reinforcement learning, which is typically used for learning from interaction. I'm coming from the interaction lab at Heriberto University in the UK, which is part of the School of Mathematical and Computer Sciences. This is the group in the interaction lab. We are researchers from all over the world, mostly including Europe, people from Europe, but also some from America and from Asia as well. We are interested in creating some sort of the next generation of interactive systems. And I'm going to give you an example of interactive system that you have probably heard about. And that's the Siri system of Apple, okay? As you may know, in this system, you can talk to the system can respond, and you can ask again, and this has been the most famous interactive system used in speech. And this is one system that we are interested in, but there are many other examples of systems that we can think about. And I will mention some of them. Another thing that all of us we're interested in is in data-driven systems. And that means systems that can induce their behavior from some data, okay? So interaction and data are two important components for the research that we carry out at this lab. And I'm going to mention some of our projects that we have. These three projects, they recently ended, and these three projects are ongoing. All these projects, they are European projects, multi-partner projects, multi-million funded projects. The partners are mostly from Europe, different countries all over Europe. And I'm going to talk briefly about the domain of each project. In the Parlance project, this is basically an information-seeking system where people can ask about restaurants in a city, right? This person is looking for some place to eat, and there are many different preferences of users, and the system has to provide information in order to satisfy the request that the user is asking for. In this system, in this system, the Spacebook project, the scenario is a pedestrian in a city. One of these cities was the city of Edinburgh. Edinburgh is famous for many different landmarks, and it's visited by many tourists all over the year. And this project developed a system for basically for tourists. In this system, this pedestrian could ask for instructions in order to how to get to places, could ask for landmarks, and the system was able also to serve as some sort of guide, okay? In this project, this is a human-robot interaction project. The scenario here is a robot bartender, a robot in a bar serving drinks to people, okay? This project was a bit similar to this one. The domain was also information seeking in terms of restaurants. This other project, Stack, the idea is more oriented to games, and the particular game that we're using is called Settlers of Catan. In this game, multiple players, they have resources, and they can trade resources in order to build cities, settlements, and roads, and they are given points for that. The player that reaches 10 points first is the winner. This project is about a tutor in a primary school with the subject of geography. So children are learning geography in this project. There's something in common in all these projects. They use reinforcement learning in order to learn from interaction. Now, it doesn't mean that all projects, they are focused specifically on that, because each project tackles a particular research question or a particular problem. So, for example, research-wise, the Poland system is interested in investigating incremental systems. In this kind of systems, the system is continuously processing input, control, and output as the user is speaking, rather than using the traditional approach of waiting for the user to finish speaking and then start processing what the users have said, right? So that's one part. Another part is investigating systems that self-extend. At some point, systems have some knowledge, but it turns out that they don't know enough of what the user can ask about, and they self-extend their domain. So self-extensible systems is also investigated here. This is investigating more situated interaction, where the user is obviously in a city. There are lots of physical objects. There are roads, there are buildings, there are landmarks, and the user is interacting via speech. The user is obviously interested in looking at the physical landmarks rather than looking at the screen, and that's why this project uses only speech. This project also uses mostly only speech. This is different because if we are talking about a robot bartender, he has to see customers that come into the bar, right? And serve the drinks that people ask for. This project investigated interaction under uncertainty, under high degrees of noise. It's typical that real environments, they exhibit different degrees of noise, and systems have to be robust to that. In contrast to processing only text, basically, when we add speech, we add a lot of complication, because we have people talking with different accents, people talking with in different environments, with different degrees of noise, through different channels, a mobile phone, a microphone array, right? In the case of human-robot interaction, it's quite challenging, because we're talking about distant speech recognition, not just speech recognition that one is talking, in a typical microphone setting. This is text-based because the game uses basically a chat box where people can type trades that they have during the game. In this game, people have to get resources in order to build their roads and cities and settlements, and there are some resources that let them build those cities or settlements, and they have to trade resources with other people. So in this project, we're investigating negotiation during the interaction. And this other project, research-wise, it investigates empathic interaction because the motive here is that if the robot uses more affection during the interaction, children can learn better rather than a robot that behaves in a generic way without any emotions at all. Okay? Okay, so again, reinforcement learning will be the focus of this talk. And I would like to give you a definition of an interactive learning machine. And that is an entity which improves its performance through interacting with other machines. We have the robot that we're trying to build, or the system that we're trying to build, and interacts with its physical world and with other humans as well. Now, in this talk, I'm gonna focus in only one machine rather than multiple machines, and only one human rather than multiple humans. So just one-to-one interaction. Something key here is improving performance through interaction. At some point, the system has some performance, but as it interacts more with the environment, the idea is that it has to improve its performance, okay? And that's why it makes it a learning machine. So if you see the difference between supervised learning, where we have a data set collected, labeled, and then we run a classifier, and then get the result. Here, the difference is that the data is coming through interaction gradually, okay? And the idea is that the system has to improve the performance over time. We will talk about how to do that. And I would like to invite you to imagine the following scenario. We have a robot that is learning to play multiple games from interaction. Now, the scenario is as follows. The robot will be giving it's a representation of the environment, okay? We will talk about how that environment is represented. And the robot also will be giving with some with a repertoire of verbal and non-verbal actions, okay? But the robot will not be given how to use them. The task of the learning system is to discover how to use these actions in each different situation, okay? So we will talk about how to do that. And well, maybe a little bit more. Why do we want to do that? Because it's complex, basically, to build a system, to hand code a system that can behave in so many different situations. The robot could face multiple users, multiple environments, again, multiple degrees of noise, and so on. We can build a system using only rules. Yes, we can do that. But again, the idea here is that we want a system that improves its behavior over time, okay? And to do that, decision making will be the key point. how to choose actions in every different situation. So that brings me to the outline of my talk. First, I will give a brief introduction to reinforcement learning. Then I will extend this framework with a hierarchical setting, which has been the main piece of work that I've been developing over the past few years. I will comment on some applications, some systems that I have particularly developed or contributed substantially and evaluated them. Some related work, where could we go based on the current state, and just provide a summary. Okay, so reinforcement learning. Interaction has been casted as a Markov decision process. And here, for some of you, this name may be familiar. This model was named after Andrei Markov, a famous Russian mathematician. And that's because these models use the Markov property that I will describe in a moment. But when one casts interaction as an MDP, we say that the environment is described with the following elements: a finite set of states or situations that describe the world of the system, a finite set of actions so that the system can do something in the world, a state transition function, and an reward function. And we can imagine this MDP with this graph. We can visualize it with this graph. Here we have an MDP with 3 states, the green nodes, and only 2 actions, A0 and A1. We can see probabilistic transitions because the transition from S0 to S2, taking action 1, involves a probability of 0.5 by taking this action and landing in state S2, and a probability of 0.5 staying in the same state. If we are here, for example, if we take action 1, we have a probability of 0.3 for transitioning to state S1, probability of 0.4 for staying in S2, and probability of 0.3, and so on. Once transitions happen, some rewards start to arrive, right? For example, the transition from this state to this state leads to a reward of +5. Here we're going to talk about numerical rewards, okay? So we can imagine reward or punishment from a numerical perspective, okay? Just numbers. And based on these numbers, the system is going to learn the behavior. So the solution for this MDP model is usually called a policy or an interaction manager. And that will be the thing that will decide what to do. And for that, we're going to use reinforcement learning. That's not the only way, but we're going to use that to arrive to the solution of MDPs. Now, another way to imagine an MDP is through this sequence of states and actions. States, actions, and rewards. So we can imagine these black nodes as choice points. And these choice points is where the system has to make a decision. Okay? And the transitions from one state to the other, we said that these are typically probabilistic state transitions, and we can see that the probability of transition into state 2 given state 1 and action 1. How do we model that? For example, we can use a Bayesian network or a similar probabilistic graphical model to model this transition function. Okay? So it sounds simple, just define these elements, use a reinforcement learning algorithm, and voila, you are done. Unfortunately, reinforcement learning is not trivial. It is trivial if we take a very simple MDP. One can implement that fairly quickly and then train it, and voila, there's the solution. But if we are talking about an interactive system where there is at least one human in the world, this world is obviously dynamic and partially known, that's not easy, that's difficult. Again, the system will be in a certain state, it will take an action, and for taking that action, it will receive a reward, and the idea will be that this agent will have to learn how to behave in the environment. Some known issues that make this topic non-trivial is scalability and partial observability. I will talk more about the first, and just about a little about the second, but this is equally important, the second issue as well. So if we imagine a robot that its world is described with binary random variables, each variable it has just two values, right? Just true or false. Is the user happy or unhappy? True or false, no? Is the user looking at you? True or false, and so on, no? So if we imagine the world described with 100 random variables, just 100, we are talking about a state space of 10 to the 30. There's a large number that if we try to visualize a graph like this for that state space is just too much, it's horrible. So we will be talking about how to deal with this scalability problem. Another way to represent the agent, the reinforcement learning agent, will be, okay, this agent will be represented with policy pi, and this will be basically a function that given one state, it will tell us what to do, and that's action A. That action A is executed in the environment in a given state that makes the transition to a next state, and that leads to a reward. And these next state and reward are given to the agent so that the agent can do some computations here, make another decision, and so on. So the goal will be to find an optimal policy, which we will denote by pi star. And the optimal policy will be basically choosing the action with the highest reward, or with the action with the highest value in this state. And to do that, we are going to refer to a Q function that specifies some values. For each state action pair, there will be a value, and again, the optimal policy will be choosing the action with the highest value in this state. That sounds simple. But again, remember that the number of states that can be huge, okay? The action set could also be larger, but typically the state space is the problem. Now, there are different ways to represent this cube function, okay? So the simplest way is to see it as a table, as some sort of matrix. When in one column we have the states, and in the other we have the actions, and in each cell basically we have the learned values. Again, behaving optimally will be choosing the best action in each state. We can use tree-based representations, or we can use function approximation, which is a much more compact version of this one, because, for example, in the linear case, the idea will be to learn some weights, given that the state space is described by some numerical features. For example, these binary random variables, they could be used here to describe something like 0 or 1, and there will be a value, a weight that will be computed by an algorithm in order to represent this state action pair. Another way to represent this is with a neural network. Some people have done that successfully, and this is easier to apply, but this is not very scalable. One can apply that to fairly small scale systems. This is more scalable, but there may be a danger that by compressing basically this policy, the behavior may not be so good. So one has to be careful that this policy is actually good. This is in the middle, more scalable than this, but not as much as this other one. Okay. Now, here we have a couple of algorithms, though just representative algorithms. There are so many algorithms. People in the literature have investigated possibly thousands of algorithms, and that illustrates how difficult it is just to do this action selection that I've been talking about. We still haven't figured out one way to do that. Some algorithms are good in some situations, and some other algorithms are good in some other situations. So one has to spot when to use what, okay? But this is a typical algorithm that has been used at least as a baseline algorithm. So one starts initializing values for this state action pairs, and then one repeats for each episode or interaction is the same. For each interaction, the state is initialized, and we will execute this until we reach a terminal state or a goal state. So what do we do in the middle? In the middle of an interaction, okay? The agent chooses an action at this state from this policy. How does it do that? There's one way that it chooses the action in a random way with some probability, and in an optimal way with some other probability, okay? This is not the only way. There are different ways. There are probabilistic methods to do this action selection. Once an action is taken, a word and the next state is given to the agent, and an Q value is computed. This is the current Q value. There's a learning rate that decays from 1 to 0 over time, and this is something called the temporal difference error. Then the next state is now the current state, and so on. Okay? So that is basically the algorithm for learning the behavior of a system. That's the simplest algorithm, but one can do a lot with this algorithm. And one can extend this one. One can see that this is a very compact algorithm. One can extend that with linear function approximation, for example, where the goal here is to learn some weights for each feature that describes the state and an action pair. For each feature action pair, there will be a weight. Again, the learning rate and the the temporal difference error, and this is the value of feature I. Okay? Again, we can think about these binary random variables. And while this algorithm could compute very large values, a very large matrix, this one computes just a fairly small vector, which could be hundreds or a few thousand values. But surprisingly, this algorithm can be quite successful. How do we compute the Q values in this form? Well, one basically does a product of feature and weight, and then we sum over all features. So these algorithms are very compact, but their application, again, is far from trivial. It's not that easy. How many of you know reinforcement learning or have applied reinforcement learning somehow? 1, 2, 3, 4. Yeah, okay. Now, so I'm going to give you an example to try to get the idea. Okay. So in this example, there will be a passenger in any of these locations R, G, B, or Y. And the goal here is that the taxi has to pick up the passenger and bring it to a target location. Okay? And to do that, we are going to represent the world with these variables, which is the taxi location, the passenger location, the passenger destination. Here, we're going to assume that the passenger can talk to the taxi, okay? So the taxi can greet the passenger. We're going to collect the destination. The passenger can also do the payment. And the payment can take these different values. And there could be a confidence score for requesting a destination or for doing the payment, basically when the passenger speaks. The confidence of the recognition confidence could be one of these three values. Now, what are the actions of the taxi? Move north, south, east, west. You can pick up the passenger, put down the passenger, ask for the destination, confirm, reject, acknowledge destination, ask for the payment, confirm, reject, acknowledge the payment, and do these greetings, hello and goodbye. So these are the actions that the taxi can do, and the idea again is that the taxi has to learn what action to choose in each different situation. And one situation is basically taking one value from these different features or state variables, okay? There are many combinations. If we multiply all these combinations, that leads to this number. 6 million state actions. For this very trivial example, okay? Here we assume that the state transitions are correct with probability 0.8, and the recognition is also correct with 0.8, probability 0.8. The reward function will be that there is a 100 for reaching the goal, and the goal will be basically bringing the passenger to the destination and collect the payment, okay? So this example basically attempts only to illustrate that even for fairly simple applications, one has this scalability problem, and this grows very quickly. And that brings me to the hierarchical setting, because the hierarchical setting is one way to tackle scalability. okay? So we want hierarchical reinforcement learning to learn a system that can carry out multiple tasks jointly, and there are several benefits by doing that. For example, this one, I know how to do that from playing the other game. And basically, this tells us that the robot learned to do something at some point, and it faces a similar situation again, and it says, oh, I know how to do that, and basically this leads to reusing what the system has learned before. And if we see, for example, a system that can play different games, one can treat each game separately, or we can see that as a single problem, optimize the whole thing, and that again leads to several benefits. To do that, we're going to cast interaction as a semi-Markov decision process, which is a generalization of the MDP model. Okay? So it's a bit similar. There are the same set of elements: states, actions, transitions, and rewards. There's one main difference, that the actions can be complex. In an MDP, actions can take one time step, and in this one, actions can take several time steps. And that's why we call them complex, because they are behaviors, they are small skills rather than just primitive actions. So to do that, we are going to model these complex actions with a different SMDP. And we can see this small hierarchy where we can have a set of games, for example, on top. In the next layer, we have the single games. In a layer under, one can have some sort of fragments of the game. And the idea is that, for example, this game is illustrating that it can use the behavior of this other game to achieve this one. Okay? So the goal here is to learn a set of policies. These I and J, they only denote one particular SMDP in the hierarchy. Okay? So basically, we will be learning one of these functions for each bubble that we can see over there. And we are going to use hierarchical reinforcement learning algorithms to do that. This is one conceptual view of a hierarchical system. In the top layer, we can see a sequence of state, action, reward, and so on. But as I said, some actions could be primitive, lasting only one time step, and some actions could take multiple time steps. So here is a child action that takes all this sequence of state, action, reward tuples, and so on. This one could have more complex actions, and so on. The benefits of having this is that we can achieve quicker learning, more scalability, and behavior reuse. I will try to extend my explanation in terms of how to achieve this, okay? Some algorithms to do that is basically an extension of the algorithms that I have mentioned before. Instead of using only Q-learning, one can use a hierarchical version of that, where the idea is to learn a Q function for each node in the hierarchy, for each bubble in the hierarchy. We can extend that also with linear function approximation, where there are this sum of products between features and weights. And we know that these weights, we can compute them in this way, as I mentioned before. Again, the main idea is to have Q functions for each behavior in the hierarchy. And some algorithms, some other algorithms are these ones, max Q and ham Q. These 4 algorithms learn basically the parameters, the values of the Q function. But one can also learn the structure of the reinforcement learning agents. And that is something similar to Bayesian networks. If people is familiar with Bayesian networks, how many people are familiar with Bayesian networks? Well, some. In Bayesian networks, one can learn the parameters, which is the probabilities in each random variable, and one can also learn the structure, and basically that's the dependencies between random variables, okay? So one can do something similar here. One can learn the structure of the reinforcement learning algorithms. Or one can provide that with prior knowledge if one has that as well. So there are some references that are added here at the bottom of the slides, just in case some people want to know a bit more about that. Okay, so now I would like to extend the taxi example, the interactive taxi, with a hierarchical setting. And we're going to have basically, we're going to break down that MDP that we described before in 9 SMDPs. Yeah. So this will be the one on top. The one on top will have knowledge about only these features. And the idea here is that this agent on top doesn't need to know the details of the entire interaction. For example, it doesn't need to know how to get from one place to another. It just needs to know where is the passenger, where the passenger wants to go, whether the payment has been collected, and so on. And some other behaviors, they can do the navigation. For example, this behavior can do the navigation to the landmark R, and this can do navigation to landmark Y. This behavior can collect the value of where the passenger wants to go. This behavior can collect the payment, and we can distribute. We can split the main task into little subtasks. Okay. Now, if we said that one agent doesn't need to know about everything, then the top agent will have only a subset of actions. How to get to a place, put in the passenger in a location, where to go, collect the payment, and so on. And so on. The navigation skills, they only need to know how to go in different directions. They don't need to know about the payment or about where to go, and so on. So by doing that, we will have smaller state action spaces, such as described here. Breaking down that original MDP into these multiple subtasks leads to only 10,000 state actions. So by only doing that, we went from 6 million state action pairs to 10,000. This basically tells us that we can solve the problem quicker we could reduce some of these behaviors, because here I'm not illustrating that, but if the passenger wants to pick up, if the taxi wants to pick up the passenger, it has to navigate, right? But if the taxi also wants to navigate the passenger to a target location, it can reduce behaviors to basically navigate, either to pick up the passenger or to bring it to a destination. And that tells us that we can reduce behaviors. We don't have to learn things multiple times. And that brings us to these benefits that I was talking about in terms of doing quicker learning, more scalability. Instead of having these large state spaces, we're going to have more compact ones, and some behavior reuse can happen. Now, I'm going to mention some applications based on this framework that I just described. Obviously, there are much more details here, but I want to give you only the main ideas. If you have questions, I will give you pointers at the end, or you can ask me, obviously, as well. Now, the kind of systems that, applications that I will be talking about, they are speech-based applications where there is a user telling something to the machine. There is some distorted speech coming into the system, some distorted understanding that is stored in some sort of knowledge base. And or we can see that as the module that keeps track of the state. This will be the reinforcement learning agent that we'll be talking about, and the one that will be deciding what to do in each situation. These actions that are taken by the agent, they are passed to a response generation component in order to generate text and the corresponding speech, so that the user can receive speech from the machine, and this basically iterates as much as needed. Okay, now this is one example for only speech-based communication. Obviously, if one has multimodal systems, one should extend this component by adding some other components, such as visual understanding, and here we can have navigation or manipulation, and basically it's just extending this this model for multimodal communication. The first application that I will be telling you about is a travel planning system. In this application, users can ask for flights, for hotels and cars. And there are two algorithms that I compare here. One is an agent that doesn't use any prior knowledge and uses this algorithm. And this is another agent that makes use of prior knowledge. By combining these two algorithms, I'm not going to describe this in detail, but I'm going to tell you that this one encodes some prior knowledge of what to do during the interaction. Often, one knows some decisions, right? Such as, for example, greeting at the beginning of the interaction. One doesn't need to have the entire set of actions, and this HAM it stands for hierarchical abstract machine, which we can see it as a probabilistic finite state machine. Sometimes it has deterministic transitions and sometimes probabilistic ones. In the probabilistic ones, the machine doesn't know what to do, and it asks the MDP what to do, okay? So basically, what we have is a joint state that what it does is basically constrains the set of actions for each situation. And yeah, so again, one that doesn't have prior knowledge and one that has prior knowledge. Reinforcement learning systems require a lot of interactions. So typically what we do is we create a model of the environment so that we can simulate interactions. Okay? So we collect some data and we use that to simulate the environment so that the agent can learn from this environment. And then we test that with real users to see whether these policies are good or not, and how good they are. Some details can be found here. This is the system that I used to evaluate those agents. I used the HTK speech recognizer, semantic, the Phoenix parser. Here I only use rule-based art recognition, a database that included information that was retrieved from the web about the domain of travel. Here are the reinforcement learning agents in the Dialog Manager. This was a role-based language generator. And I use the HTS and Festival speech synthesizer, all brought together by a middleware called Open Agent Architecture. So that was several years ago. I evaluated that. And here's one example of these learning agents. The blue line is flat learning. That means one single MDP. In the x-axis are number of interactions, and the y-axis is basically interaction length. How long are the interactions in terms of time steps? The lower the better here. Here we can see the effect of adding the hierarchy. Adding a hierarchy leads to quicker learning. This blue line is a reasonable hand-coded behavior. Details again are here. And this other one is this one extended with prior knowledge. And one can see that learning can be substantially quicker. Here we have just a couple of hundred interactions rather than using flat learning without any single prior knowledge that requires 100,000 interactions. So some results that we can see from here is hierarchical reinforcement learning finds solutions faster than flat learning. Hierarchical reinforcement learning is more scalable than flat learning, and that learn policies outperform hand-coded ones. Something that we can see from here is that even policies using prior knowledge, they can outperform hand-coded ones. And that's interesting, because that tells us that if we use this framework to optimize interactions, one can build systems that can achieve higher performance. Okay. Okay. The second application is an indoor wayfinding system. The scenario is as follows. There is a complex building, where academic people work and study, and there are infrequent and new visitors to this building, and they often get lost. And the idea of this system was to create an InfoQ system so that users could ask for route directions in terms of how to get to a particular place that they were looking for. Okay. So it's wayfinding assistance, and here I'm comparing two algorithms. One algorithm that doesn't make use of policy reuse, and one that makes use of policy reuse. Some policies, they were learned beforehand, and during the interaction with the users, they were reused in order to do very fast learning. So basically, the idea here was that the agent had to learn to navigate users on the spot. When the user typed, "I want to go to this place," the system had to learn how to guide the user. And so we had situations where the system had to detect where the system knows how to act, and when the system doesn't know. In the case where the system knows how to act, it could use an optimal policy. Otherwise, it could use an exploratory policy. Training was carried out with simulated interactions, and testing with real users. So this is the architecture of this system. There was a graphical interface. We had two versions of that system. One was an info kiosk where the user typed in a screen the request, how to get to a particular place. Another interface was a mobile phone. Well, as the user was navigating, it could get route instructions, right? So it was touch-based. There was some language understanding here, knowledge base. This was the interesting part because this was the component integration, the reinforcement learning systems. This reinforcement learning system was aware not only of verbal actions, but also of the spatial environment, okay? Why? Because actually some users, they used to get lost at some particular points, and the idea is that the system should guide them in a way that users shouldn't get lost, through the routes that users don't get lost. There was some language generation to generate the route instructions, and some details, they can be found here, okay? So we have been saying that reinforcement learning systems, they have to improve the behavior over time. Here is one plot that illustrates that over time the system is, here we have two situations, one without policy reuse and one with policy reuse. They are both improving their behavior over time. As the more interactions, the better. Here, the higher the reward, the better. We can see that if we make use of policy reuse, one can make a substantial difference in terms of amount of interactions needed for learning the behaviors. So if we don't use, in this particular case, policy reuse, the system requires several thousand interactions. And if it makes use of policy reuse, less than 100 interactions is actually needed here. Again, the details of the state action space reward can be found here. The results that I can tell you about is that policy reuse finds solutions faster than without it. I guess that's obvious, but something interesting is that adaptive route instructions are more efficient. Route instructions that are more suited to particular users seem to be more efficient. Why? Because the system is trying to find route instructions that are less prone to getting the user lost, okay? So navigating the user without the user getting lost was important here. And again, this enable us to run learning on the spot. while the user was typing the request, learning was actually very quickly. This one wouldn't be able to let us do that because it requires more time. Okay. Now I'm going to tell you about a different application, the last one, and this one is about human-robot interaction. This one will highlight one of the limitations of breaking a problem into the problem. And it turns out that by breaking the problem into the problems, we said, well, that's actually good. That leads to quicker learning and is more scalable. But it turns out that during the interaction, users can talk about different things. And at some point, the interaction could be here, but immediately it could be here. And we observed that actually what was needed is some sort of non-strict hierarchical control. Although we can execute these behaviors from top to bottom, we can start from a root interaction and then call a sub dialog. Once this one terminates, it can go to the parent and so on. But sometimes one needs to go from here to here directly. So that's why I'm contrasting here hierarchical, strict hierarchical control and non-strict hierarchical control to add flexibility in their interaction, okay? So that the user, if we imagine this travel planning application, at some point the user is booking a flight, but immediately it could say, oh, I want to change my hotel booking. And go back and forth, right? If it's playing a game, it could say, oh, I'm bored and now I want to play this other game. And you know that the system has to be flexible. Or within a game, it could also jump from one subdialog to another one. So here what I'm comparing is two algorithms. One that makes use of this form of control from top to bottom, and the other that extends that form of control with non-strict hierarchical control. Training is also with simulated interactions. There are some interactions collected beforehand. A model is trained from those interactions so that the agent can interact with this trained model. And then the learned behavior is tested with real users. This is the system that was used for that particular application. It was just a quiz game, just a game where where users can ask questions to this robot, and vice versa. The robot can ask questions to the person. Okay. So there was an interaction manager that only had a small hierarchy, one top controller, two subcontrollers, one for asking the user questions and the other for responding, basically. There was a user model that kept track of what people have asked, have answered before, and there was a language generator that was used to generate the text conveyed by the robot, a speech synthesizer, a motor control component that was used to basically move the body of the robot, a speech recognizer. Voice activity detector also was important because one needs to know when the user is speaking and when the user is not speaking, okay? A gesture recognizer. We didn't use much this gesture recognizer for this game, but for other games it was used much more. In this one, there are not many gestures happening during the game, but there are some other games that have more gestures. A parser to know what the user, the meanings of what the user is talking about. We use these Wizard of Oz to collect data, and one component that knows about the domain of the game, all brought together by a middleware provided by Aldebaran Robotics. Details are here in this publication. So here we can see some results. Here we have number of interactions. We have average reward, the higher the better. We can see the blue line executes strict hierarchical control, and this other one executes non-strict hierarchical control. In simulation, we can see that flexible interactions are better, and we can see here, these are results from real users, where we ask a number of questions, but when one takes all these questions overall, we can see that non-strict hierarchical control leads to higher user satisfaction than only using strict hierarchical control. So the results here are non-strict hierarchical control leads to more natural interactions, and non-strict hierarchical control is also preferred by human users. Again, some results are here, and details, obviously. And I would like to show you an example of these interactions. These results are actually results derived from adult users that play with the robot. But we also use that in a hospital where children, hospitalized children, they were able to play with the robot. And here I would like to ask somebody to play the video, please. Yeah, it's coming.
Se ti capita di avvertire un incompleto a scuola, devi correggere con zucchero nel quale incomincia una. Vero o falso? Sbagliato, no. Era vero. Perché se tu ti senti male devi mangiare lo zucchero. Ok, tocca a me. Va bene, no? Ritratto. Posso riprovare? Sì, grazie, no? Sei gentile. Va bene. Visto ti vuole bene in più ancora. Ok. Posso fare una domanda? Va bene? Sentite. Perché bisogna masticare del cibo prima di mangiare? Anche io ti voglio. Allora, perché bisogna masticare del
Okay, I guess we can stop it here. This is another child, but you get the idea. Users speak differently. Maybe let's play the next one to see a bit more, to see a different user. Why not?
Durante un temporale, cosa arriva prima? Il lampo, il sole. Giusto. Allora, tanto. Sì.
Okay, I think we can stop it there. Can we go back to the slides, please? So, we saw that with only these two uses, we can see different ways of interacting, right? Maybe one of them is one speaks very quickly, the other speaks slowly, and one can see immediately that machines have quite a challenge. They are using the same environment. Actually, this is a quiet environment, but how about if the environment is noisy? How about if there are multiple children? And so on. We could imagine multiple scenarios where handling interactions that are meaningful is actually difficult. And coding a system, yeah, one can do that to some extent. But again, there are so many situations. If we want behaviors that take fine-grained decision-making in all these different possible situations, then possibly you can see that learning machines make sense so that they can discover what to do in all these different situations, okay? Even for some small domains, such as just a quiz game. Just a quiz game can be quite challenging, again, in order to achieve meaningful interactions with real people. Now, so some related work. Obviously, other researchers have tackled the problem in different ways. Initially, if we see learning with large state spaces in only two dimensions, we can see optimality and scalability. Initially, people target only flat learning, a single reinforcement learning agent. And if one wants to deal with large state spaces, there are basically two ways. One is breaking the problem into problems, and that means using hierarchical reinforcement learning or using function approximation. Some people have made use of function approximation to do that, but again, with only one learning agent. And I've been putting these two together in order to achieve more scalability. Because again, one can learn multiple behaviors. These behaviors can benefit each other from reducing their behavior, and if they know about how to solve a particular subproblem, I guess that's good, because they can learn faster and they can be reduced in the future. And the kind of systems that I have been using so far, they are still fairly small because they don't tackle many different subtasks. It could be nice a system that can learn to do many different things, and policy reuse could be even more prominent, but that still needs to happen. Another one is learning under uncertainty. I didn't speak about uncertainty, but people have tried many different ways to tackle the problem with this model, which is called the partially observable MDP, or POMDP, famously known as POMDP. Again, people have done a lot of progress with this using a single reinforcement learning agent. And what I have done is I have put Bayesian networks with semi-markup decision processes in order to target scalable solutions, but that they can handle some degree of uncertainty, but by maintaining the state space in a Bayesian network so that it can tell me what's the probability of being in this situation, okay? And And by doing that, then given the most likely situation, an action is chosen, and so on. The reinforcement learning algorithm has to learn to decide what to do. But again, there are a lot of publications around this model, and possibly in the future, hierarchical POM-DPs, they also should be explored. And that brings us to a wider spectrum of Markov decision process models, of Markov process models. So we can see this cube, where here is basically whether the agent can control the interaction. Here is whether the agent has hidden states or non-hidden states, flat representations or hierarchical representations. I talked basically about these two corners, MDPs first and then SMDPs. I have said that people have done a lot of work in this corner, but there is this corner that still remains to be explored. And I believe that if we move to these corners, that is more promising for systems that they represent larger scale systems, that they can optimize multiple tasks in a unified way, rather than totally independently. So for the details of these Markov process models can be found in this reference. Okay, so some future directions based on the current state of the world. I listed these 7 directions. It doesn't mean that these are the only ones, but these are some that I think could lead to future interactive learning systems. So the first one is we need a big effort to make the system perform similar tasks. If I have a quiz system and I want to extend that system to handle some similar tasks, there's a reasonable amount of effort that is required to actually do that. The system has to relearn. Well, first of all, it has to add possibly new features, new actions, possibly a new hierarchical representation, and training. More data needs to be collected, training, and there's a lot of effort needed for that. And we still don't know how to build systems that are more flexible and that can self-extend. Okay. Simulations. The systems that I talked about, they may represent the world in some situations because it depends under what conditions I collected that data. If I collected the data in my lab, that may not be the same case in the real world. Okay, so that could be fine sometimes, but sometimes that is these simulations need to be basically accurate in terms of representing the real world where the agent will behave. We often don't know how to specify the reward function. In the taxi example, it's fairly simple that once the taxi has achieved the goal, one can give a big reward for that. And but in some other situations, for instance, in the quiz game, how do we specify the reward function? I specified a reward function based on correctly answer questions, but it doesn't mean that that's the way. It could be a reward function based on how happy the user is. So basically, for example, one could have a detector of affective states to see whether the user gets happy or unhappy, and these could be the source of rewards, right? But again, sometimes it's not easy to define the reward function, and we still need to do some work in that direction. The real world is partially known and dynamic, so our systems, many times they can handle a fixed world, but they cannot handle a dynamic world. Okay? Many systems, they have poor spatial cognition, they don't know much about space, and that's because encoding features of the space that represent the world is not easy, and also one needs to do more work in that direction if one wants situated interaction. Small vocabularies discourage talking to machines. Many times systems, they use a fairly compact vocabulary, and that leads to also compact meanings that the system can understand. If one has a small repertoire of meanings that the system can understand, then that could be a limitation, because the machine many times wouldn't understand, okay? And if the machine exhibits more understanding, it could lead to better user satisfaction, for example. And finally, there is a lack of interactive learning systems in the real world. Siri may not be an example of these learning systems, because I have heard that Siri uses a lot of prior knowledge, a lot of rules to handle the interaction. So, again, interactive learning systems in the real world, they are not there yet, or at least I'm not aware of. Let me know if you know of some systems. These systems are still in the labs, and these systems need to go out of the labs into the real world. So that's something that remains to be done. The list that I mentioned before possibly brings us to think that we need systems with more autonomous interaction. Why? Let's look at these systems from two dimensions: the amount of tasks that they can handle, and the degree of autonomy. By autonomy is basically that the systems, they decide what to do on their own, right? Many systems, they can handle only one task, or very few ones. But it remains to be done to achieve systems that can handle multiple tasks. And if in parallel, these systems, they become autonomous, then that will be a point where future interactive systems will be autonomous. This is I think, is the current world, because current systems, they need a lot of human intervention. To build an interactive learning system, it means a lot of human intervention so far. And systems that self-extend, which is towards this direction, still remains for the future. And one question is, how do we get there? And one point that we can make is that we need a holistic perspective from different disciplines, from language, from vision, from robotics, from psychology, from not just from these fields, cognitive science and so on, human-robot interaction and so on. So finally, I'm going to conclude. Machines can be programmed to behave just as expected. We know that. But I believe the physical world and humans demand systems that can learn, so they can achieve more adaptive and robust behavior. To do that, and so that systems can deal with this partial observability and dynamic worlds, those systems, if they use some sort of hierarchical mechanisms, I believe that they play an important role for large-scale systems and robots. More autonomy is needed if systems are to learn new skills with little human intervention. Currently, we said that the systems, they require a lot of human intervention. in terms of system development. And a holistic perspective is needed for building the next generation of intelligent interactive robots. The work that I described can be found in these 3 different journal papers. And here's my email address. In case people have some questions, you can mail me in the future. Thank you very much.
Human representation, in such tasks as interactions with humans and especially involving empathy with children.
Yeah.
It seems to me that it would be logical and from the psychology perspective as well to use some kind of representations of human objects with children involving emotions and other different stuff.
Yeah.
We have tried this, so
yeah, no, unfortunately, I haven't done work with affective interaction. Some of our partners, they have done some work, but personally, I haven't done work with affective interaction. The systems, for instance, the quiz game that I mentioned, it makes use of some motor control mechanisms that are effective in terms of getting sad or happy, but these were done by one of our partners. I am more, my work is more in the learning mechanism in terms of putting everything together and making the behaviors happen, but studying the behaviors from an effective interaction, that's something that I haven't done. And the state representations that these systems have used, they are still very compact. They don't encode much effective interactions. Yeah. And the project that I mentioned at the beginning, Emote, that's a project that is actually targeting that. Is targeting the study of effective interaction and how that impacts education, for example. But that's a work in progress. Yeah.
Thank you. How about systems that involve any other features of people or other
Yeah.
objects in the world?
Yeah. Yeah.
Involve these features in a hierarchy.
Yeah. Yeah. Yeah, thank you for, yeah. So the systems that I described, they use features provided by somebody. They are not features induced automatically. It would be nice if, for example, the robot is able to acquire some features and incorporate these features in its knowledge. But I can say that for the future. In these systems, one provided the set of features beforehand. This is the current representation of the world, and but that can be learned. That can be also learned. One can use, as in other forms of learning, some sort of feature selection, because we can say, okay, there's all this bunch of features, but use the features that are only useful for optimizing the interaction. Feature selection is something that also I didn't do, but that can be done as well.
Any short questions? Short.
Yeah.
Thank you, very exciting. What I've seen here where you've shown the example of hierarchical learning. You've basically broken down the task, a longer task, into subtasks, and that looks like cheating to me. So you basically solved the problem for the robot, for the agent. So the agent will never, for example, the taxi driver example, it will never stop in the middle of the road and say, okay, pay now, I'm not taking it further. So that's it cannot learn this behavior from the framework you've given it, right? So have you thought about allowing the system to think of ways of how to break down the tasks? You know what I mean? Thanks.
So we can see hierarchical learning. An analogy could be programming. If we don't use a hierarchical setting, we would have to write very long programs, right? And we don't do that. We use modular programming typically. We break down problems naturally, and that's a natural way of solving a problem, right? If we can also think about this. You are trying to do something on the weekend. You break down and you are trying to come up with a plan, right? Initially, you think about the high level in terms of saying, okay, where can I go? You still don't think about how to get there, right? You still just think about the high level solution. So one naturally develops plans at different levels of granularity. And there are some references that actually say that the brain, it actually processes information in a hierarchical setting. The hierarchical setting, one can specify the hierarchy, or the hierarchy can also be learned. As I said, in Bayesian networks, we do that. Well, some people, they specify manually the dependencies among random variables, right? But the structure can also be learned, and especially for complex systems, that's needed. So again, hierarchy seems to be something natural that tackles the problem of large-scale systems. That seems to be the way the brain works, and one can do that manually or automatically. So yeah, I hope that I answered your question, but otherwise we can talk offline.